Back to the deep dive. So if you've ever used these big language models for, really complex stuff, writing long reports, big coding projects, maybe even logic puzzles, they're amazing, but man, they can be slow. It feels like they're just plodding along one word, one token at a time.
Yeah, exactly. That sequential step-by-step thinking is fundamental, but when the task needs a lot of steps, you really feel the weight.
Right. And people have tried speeding things up, usually by getting multiple models involved somehow.
There are definitely approaches out there. Like you might have several models solve the whole thing independently and then, vote on the best answer.
Okay, the wisdom of the crowd approach.
Sort of. Or you might have one model act like a manager, breaking the task down and assigning subtasks to other models to do in parallel.
Like a typical team project structure.
Exactly. But those methods have real limitations. Voting means tons of wasted effort, right? Everyone does the whole thing.
True.
And splitting tasks only works if the plan is perfect up front and nothing unexpected happens. If one worker hits a dead end or finds a shortcut, the others are basically flying blind.
Because they're working in their own little silos.
Precisely. There's no good way for them to share discoveries as they happen.
Yeah, not like how humans collaborate. We're constantly seeing what others are doing, sharing ideas, changing plans on the fly.
That dynamic aspect is key, and that's really the core challenge tackled in the research paper we're diving into today. It's called Hogwild. Inference. Parallel LLM generation via concurrent attention.
Hogwild inference. Okay, that sounds energetic, maybe a bit chaotic.
Well, it's controlled chaos, you could say, in a really efficient way. Our goal here is to really unpack this paper, get into the nitty-gritty of its core technical innovation, and see how it lets these LLMs collaborate dynamically, almost like they're sharing thoughts in real time.
And that's where the real academic contribution lies, right? And how they enable that dynamic sharing.
Exactly. It's not just parallelism, it's enabling a new kind of parallel interaction.
Okay, let's get into it. The big problem is enabling this dynamic real-time collaboration during inference. How does Hogwild actually do it?
So the main idea is pretty elegant, actually. You run multiple copies instances of the same LLM. They call them workers.
Okay, multiple workers, same brain.
Right. But here's the twist. They all access a single shared memory, specifically a shared key value cache, the KV cache.
Ah, the KV cache. That's the model's internal scratch pad, right? Where it keeps track of what's been said already so it can pay attention to relevant history.
Exactly that. Normally, every LLM running separately has its own private KV cache. A big innovation here is making one cache that all the workers can read from and write to concurrently.
Concurrently. So as one worker generates a token and calculates its KV representation,
it goes straight into that shared cache, and another worker running in parallel can immediately see that new token's representation and attend to it, and vice versa.
Wow. Okay, so they get instant visibility into each other's train of thought as it's forming.
That's the idea. It's like they're all thinking out loud in the same room and everyone can hear and react instantly. The name Hogwild, by the way, comes from parallel computing.
Oh.
Yeah, it refers to a style of algorithm where multiple processes access shared memory without strict locks, just grabbing updates whenever they're ready. It kind of captures that concurrent, unsynchronized access vibe.
Okay, conceptually that makes sense. Instant sharing enables collaboration. But technically, sharing a KV cache sounds incredibly tricky. Each worker is generating its own sequence. How do you deal with positions? A token from worker Bob is at, say, position 50 in Bob's sequence, but from Alice's perspective, looking at the shared history, it might appear much later. Right?
You've hit on the absolute core technical challenge, and solving this is really the breakthrough that makes Hogwild work efficiently.
Okay.
Because the naive way, like having Alice constantly recalculate or re-encode Bob's KV entries to fit her sense of position, that would be a computational nightmare. The cost would blow up, probably scaling cubically or worse with the number of workers involved. Just totally impractical.
Right, that would completely defeat the purpose of speeding things up. So how do they get around that? What's the trick?
They found a really clever solution by exploiting a property of Rotary Position Embeddings, or ROPE, which, most modern LLMs use anyway to encode position information.
ROPE, right. It applies rotations to the query and key vectors based on their position.
Exactly. And ROPE has this neat mathematical property. The dot product in attention, which measures how much a query should attend to a key, is invariant to relative rotations.
Okay, say that again. Invariant to relative rotations.
Yeah, so imagine you rotate the query vector by angle A and the key vector by angle B. The dot product between them is the same as if you just rotated, say, the query by the difference in angles A minus B and left the key alone. Or vice versa. It's the relative rotation that matters for the final attention score.
Huh. Okay, I think I follow the math property. How does that help here?
Well, instead of trying to rotate all the past KV entries from other workers in the shared cache to match the current worker's absolute position, which is the slow part, they do something smarter. They keep the KV entries stored in the cache fixed, basically tagged with their original position within the block they were generated in.
Okay, so the cache entries stay put.
Right. Now, when worker Alice needs to attend to a token generated by worker Bob in a different block, she calculates the positional difference, the relative distance between her current query position and the position of Bob's token in the shared cache.
And the clever bit.
She applies the necessary rotation based on that relative distance only to her current query vector.
Ah, so she rotates her query to match the relative position of the key instead of rotating the key itself.
Exactly. And because of that rope property, the resulting dot product is mathematically equivalent to if she had rotated everything to absolute positions. But computationally, it's vastly cheaper. You're just rotating one vector, the query, multiple times, perhaps once per block you attend to, instead of potentially millions of key vectors in the cache every single step.
Wow. Okay, that is clever. You rotate your viewpoint essentially based on how far away their contribution is in the shared timeline, rather than trying to shift all their past contributions into your current timeline view.
You got it. That's the core technical insight that unlocks efficient shared KV cache access. They built this using, optimized custom kernels, drawing on ideas from things like flash decoding and paged attention to manage the memory efficiently on the GPU, so you only store one copy of each KV pair, and the query rotations are handled fast.
That's a really elegant solution to the scaling problem. But okay, even if the mechanism is efficient, just dumping every single token from every worker into one massive, shared history might still be a lot, especially for really long, complex problems. How do they structure this shared space to keep it manageable?
Good point. And they thought about that too. They introduced a structure inspired by basically a group chat room.
A group chat. Okay.
So they don't just treat it as one long sequence of tokens. They group the output into reasoning steps. Think of these like paragraphs or distinct chunks of thought, usually ending with a full sentence and a double new line.
Okay, structuring the output into logical blocks. Makes sense.
Yeah. And the shared memory then has sort of two main parts. First, there's a common cache. This is like the main chat history that everyone sees. It holds the initial prompt plus the history of all the completed reasoning steps from all the workers.
So the finalized paragraphs go there.
Right, added chronologically as each worker finishes their step. Second, each worker has its own little individual cache for the reasoning step it's currently working on, the unfinished paragraph.
Okay, a shared history of finished work and private scratch pads for current work.
Almost private. As a worker generates tokens, they go into its current step cache. And this is crucial for the dynamic part, workers can instantly see each other's current unfinished steps too.
Ah, how does that work?
When a worker does its attention calculation, the context it sees is the common cache history, then its own current step, and then the current steps of all the other workers appended right at the end in real time.
I see. So you get the long-term memory of completed steps plus this immediate window into what everyone else is typing right now.
Exactly. It's the best of both worlds, stable history and instant awareness of ongoing work. Then, when a worker finishes its step, hits that double new line, its completed steps KV entries get moved from its individual cache into the main common cache, with the positions adjusted correctly using that rope magic, and its individual cache clears, ready for the next step.
That layered cache structure, common history plus visible current work, sounds really effective for managing the flow of information. Okay, so you have the technical means to share memory efficiently, structured intelligently. But the models themselves weren't trained for this kind of teamwork, right? How do you actually get them to use this shared space effectively?
Right, that's the zero-shot challenge. They haven't been fine-tuned to be collaborators, so the key is clever prompting.
Okay, what kind of prompts?
They use a system prompt initially to set the scene, give the workers names like Alice and Bob, tell them they're a team, they can see each other's work in this shared space, and explicitly encourage them to coordinate, maybe divide up the problem, check each other's logic, and importantly, try not to do the same work.
Setting the rules of engagement, basically.
Yeah, but just telling them isn't always enough. Reasoning models can sometimes get really focused on their own line of thought, right? Tunnel vision.
Sure.
So they added a specific periodic intervention. Every so often, say after generating 1024 tokens or so, one worker is randomly chosen. And at the start of its next paragraph, it gets this prompt inserted. Wait, am I doing redundant work? Yes, no.
Ah, that's direct. Just forcing it to pause and check.
Exactly. It's a nudge. It forces that worker to stop its internal monologue, look around at the shared context, especially what the others are doing right now, and make an explicit judgment.
And does it work?
Apparently, yes. The paper shows examples where this prompt makes a model realize, oh, wait, Bob is already calculating that intermediate result, respond yes, and then pivot to working on a different part of the problem.
That's fascinating.
Or sometimes it confirms, nope, what I'm doing is unique and necessary, responds no, and carries on. It's a really neat, simple trick to leverage the shared visibility more reliably.
So you've got the rope trick for the efficient shared memory, the group chat cache structure, and this prompting strategy for zero-shot collaboration. It all sounds very promising. How did it actually perform in their experiments? Did the models collaborate? Did it speed things up?
The results are pretty compelling. First off, they observed that modern reasoning models, they tested llama variants, Mixtral, etc., can effectively use this shared cache to collaborate without any special training.
And what did that collaboration look like? What kinds of behaviors did they see?
They saw models doing things like formulating plans together, adapting those plans when one worker found something new, even pointing out errors in another worker's reasoning.
Wow.
And using each other's intermediate results, and importantly, detecting and avoiding redundant work, especially spurred by that intervention prompt.
Okay, so the qualitative behavior suggests the system works. What about the hard numbers? Performance, accuracy.
Right. So they measured accuracy versus computational cost, basically, how many forward passes the models did in total. On tough reasoning benchmarks, like a complex logic task called LIMO and also math problems, Hogwild consistently got higher accuracy for the same amount of compute compared to standard baselines like self-consistency, where you just run it multiple times independently, or skeleton of thought.
So smarter collaboration leads to better answers for the same thinking budget.
That's the idea. And accuracy generally went up as they added more workers, going from 1 to 2, 3, or 4 workers, showed clear benefits over the single worker or baselines. It shows the parallel collaboration is genuinely helping.
Okay, that's accuracy per compute. But the really exciting part for practical use is raw speed. Right? Does it actually solve problems faster in terms of wall clock time?
This is probably the most striking result, practically speaking. Yes, it does, significantly. They benchmarked it on real hardware, an NVIDIA L40S GPU. And they saw huge speedups in terms of tokens generated per second. It scaled almost linearly with the number of workers. With 2 workers, it was roughly twice as fast as 1. With 4 workers, it was about 3.2 to 3.6 times faster.
Whoa, nearly linear speed up in actual time. That's huge.
It really is. It means the accuracy gains aren't just theoretical. They translate directly into getting the answer much, much faster. The overhead for managing the shared cache and doing the rope query rotation seems pretty small compared to the massive win from parallel generation.
That makes it incredibly practical.
Absolutely. And this speed up seemed to hold across different model families and different types of problems, math, coding, physics. They did mention smaller models were sometimes less stable, suggesting you need a certain level of reasoning capability for this zero-shot collaboration to really click.
That makes sense. Did they try to quantify the quality of the collaboration itself?
Yeah, they did something interesting there. They used GPT-4 OA as an external judge to read the interaction transcripts between the workers and score how collaborative they seemed.
Okay.
And they found that the full Hogwild.setup, with that instant token-level visibility of current work, got significantly higher collaboration scores compared to alternatives, like only syncing completed steps or having no shared context at all.
So that real-time awareness really is the key ingredient for enabling the dynamic teamwork.
It seems to be, yeah. That shared concurrent attention is critical.
It's a really strong package of result. What about limitations? What did the authors acknowledge?
The main things they noted were, as I mentioned, maybe reduced performance or stability with smaller models. Also, potentially issues if the context becomes extremely long, although the step-based structure helps mitigate that. And the fact that they used the proprietary GPT-4o for judging collaboration makes that specific part hard for others to reproduce. Exactly.
All fair points. And where do they see this going? Future work?
Lots of interesting directions. Obvious one is fine-tuning models specifically for this kind of shared memory collaborative environment that might really boost performance, especially for smaller models.
Training them to be better teammates.
Right. Also combining Hogwild with other parallel techniques like speculative decoding. And then there are more exploratory ideas like using the shared memory concept, not just between LLMs, but maybe for asynchronous collaboration between a human and an AI.
Whoa.
Or even letting LLMs interact with tools or a file system through a shared memory interface.
That human-AI shared workspace idea, that feels like a big leap, but this research definitely makes it seem less like science fiction.
It certainly opens up the design space.
Okay, so let's wrap this deep dive up. The core innovation in Hogwild, inference is really this shared, concurrently updated KV cache.
Yep, letting multiple LLMs essentially share a common short-term memory.
Made practical by that clever rope trick, rotating the query based on relative position, not re-encoding all the keys.
Which avoids that computational bottleneck.
And structured effectively using that group 10 idea, a common history of completed steps, plus real-time visibility into everyone's current work.
With prompting strategies like that "are you being redundant" nudge to make the zero-shot collaboration actually happen.
And the payoff is pretty huge. Existing powerful LLMs can team up effectively right out of the box. They achieve better accuracy for the same compute.
And, crucially, deliver near-linear speedups in actual inference time, getting complex answers faster.
It's a really powerful demonstration that if you give these advanced AI systems the right kind of communication channel, this shared mental workspace, they can spontaneously figure out surprisingly sophisticated ways to work together.
Exactly. The collaboration emerges from the interaction enabled by the shared context.
Which leads to maybe a final thought to chew on. If just providing shared memory and real-time awareness unlocks these kinds of emergent collaborative strategies in LLMs without explicit training for teamwork, what does that tell us about how collaboration itself might arise in complex systems, artificial or even biological? And thinking further ahead, could future AI teams linked by even richer shared environments or senses develop entirely new forms of collective reasoning or problem solving that we can't even quite imagine yet?
It definitely makes you wonder if the key to advanced AI collaboration is less about painstakingly programming the rules and more about building the right shared environment for awareness and interaction to flourish.
A fascinating glimpse into making AI not just smarter, but better at working together. That's all the time we have for this deep dive.